Determination of M and BH using box type vibration magnetometer and SEARLE'S vibration magnetometer. Our aim is to determine the magnetic moment and S magnetic field at the given place using box type and SEARLE'S vibration magnetometer. Now, the box type vibration magnetometer, this one is the box type vibration magnetometer, that consists of a bar magnet which is kept over a stirrup. Now, this is a stirrup, and this stirrup is suspended by means of a torsionless fiber inside a tall jar, and that magnet is kept inside a wooden box with glass windows, so that there is no other disturbance from the outside, no wind etc. are not blocking the magnet movement. When the magnet is oscillating, we can find the time period of oscillation, that is the use of the box type vibration magnetometer. Similarly, the SEARLE'S vibration magnetometer, now this is the SEARLE'S vibration magnetometer. Now, the SEARLE'S vibration magnetometer consists of a small magnetic needle, we can see here that red and black one, that small one, the small needle down, that is kept on a cylinder, and that cylinder is suspended with the help of a silk torsionless fiber. The height can be adjusted. Now, when it is in a particular magnetic field or in the earth field, that is oscillating, now it is oscillating, we can find the period. Now, to take the measurements or to observe the deflections, we are using an aluminum pointer. You can see that is the long one, that is kept just over horizontally over the small magnetic needle, that is the aluminum pointer, and the suspended magnet is kept inside a glass jar is there, that is also to avoid the outside disturbances, that is the SEARLE'S vibration magnetometer, and we are using this box and SEARLE'S for this particular experiment. Now, let us discuss the theory involved in the determination of moment of a magnet and the horizontal component of S magnetic field BH using box and SEARLE'S vibration magnetometer. We are having a box type vibration magnetometer and a SEARLE'S vibration magnetometer, and for the box type vibration magnetometer, if it is permitted to oscillate in the Earth's field, the period of oscillation T is given by the formula 2 pi root of I by MBH. That means the period of oscillation is proportional to, or square of the period is proportional to the moment of inertia I of the magnet, and inversely proportional to the moment of the magnet and inversely proportional to BH. Where for a rectangular magnet, the moment of inertia I is given by mass of the magnet into the length square plus breadth square, plus breadth square divided by 12, that is not minus, that is L square plus B square by 12. So, that is the value of I. And again, for the box vibration magnetometer, B is equal to, from the principle of box type vibration magnetometer, B is equal to BH into T1 square minus T2 square by T2 square, where T1 is the period of oscillation of the SEARLE'S vibration magnetometer when it is kept in the S magnetic field BH, and T2 is the period of oscillation in a combined field. That means the SEARLE'S vibration magnetometer is placed in a field B, then the total field is B plus BH. At that time, the period of oscillation is T2. Then from the principle of SEARLE'S vibration magnetometer, B is equal to BH into T1 square minus T2 square by T2 square. But in the case of SEARLE'S vibration magnetometer, we are keeping the magnet along the north-south direction. Then the SEARLE'S vibration magnetometer is on the axial line of the magnet, and the magnetic field produced on the axial line of a magnet is given by the formula B is equal to mu 0 by 4 pi 2md divided by d square minus L square the whole square. So, in the equation 1 we can substitute this value of B, then we obtained mu 0 by 4 pi 2md divided by d square minus L square the whole square is equal to BH into T1 square minus T2 square by T2 square. From that equation, we can write the value M by BH, M divided by BH we are calculating. So, M by BH becomes 4 pi by mu 0 d square minus L square divided by 2d T1 square minus T2 square by T2 square. So, that is a formula to calculate M by BH. Now again going back to the equation 1, that is MBH we obtained because we are squaring the equation, that is T square is equal to 4 pi I by MBH. From that MBH is equal to 4 pi I by T square. So we are having two equations now. One is MBH. MBH is 4 pi I by T square, and this MBH is written as x. This MBH is written as x, and this M by BH is usually written as y, and that M by BH is calculated using this formula. So we are having MBH as x and M by BH as y. Then using that too, if you multiply x into y, x is equal to MBH and y is equal to M by BH. So x into y is BH and BH cancel, that is M into M, that is M square, where M is the moment of the magnet. So we can calculate the value of M. M is equal to root of xy. So we determine the value of x. X is MBH, that is 4 pi I by T square, and y is M by BH is calculated using this formula. Knowing the value of x and y, we can determine the moment using the formula root of xy. Similarly, if we divide x by y, now x is MBH and y is M by BH. Now if we divide, we are getting what happens, M and M cancel, this BH goes to numerator, so we are getting BH square, or we are getting BH is equal to root of x by. So BH is horizontal component of S magnetic field. So we can calculate BH using the formula root of x divided by y. We already mentioned what is x and y. Substituting that value of x and y, we can determine the value of BH. Now coming to the procedure, initially we are using the box type vibration magnetometer alone. The magnet is suspended and it is allowed to oscillate in the Earth's field. The period of oscillation T is determined and we obtain the period. And then we are using the SEARLE'S vibration magnetometer, and before that for the box type vibration magnetometer we can calculate the quantity MBH, because MBH is equal to 4 pi square I by T square, where I the moment of inertia that we calculated, T we now obtained. So we calculate the value of x, that is MBH is calculated. Now we want to calculate y, that is M by BH. For that we are using the SEARLE'S vibration magnetometer. Initially the SEARLE'S vibration magnetometer is placed along the north-south direction and only in the Earth's field. It is allowed to oscillate. The period of oscillation T1 is determined. So T1 is the period of oscillation of the SEARLE'S vibration magnetometer in the Earth's field. Now a magnet is kept either in the north side or in the east side. Now it is placed in the north side at a distance say d from the center of the SEARLE'S to the center of the magnet. The distance d is measured. The magnet is kept. Now there is a combined field is acting. Now in that combined field we can find the period of oscillation, and that period of oscillation is T2. Now it is repeated, keeping the magnet on the other side also, keeping the north pole pointing north. So the two fields B and BH are added. The period is again determined. The mean of the period is calculated, that is T2. So we obtain T2. So knowing this value of T1 and T2, we can calculate M by BH using the formula 4 pi by mu 0 d square minus L square divided by 2d into T1 square minus T2 square divided by T2 square, where we mentioned d is the distance between the center of the SEARLE'S to the center of the magnet. L is half the length of the magnet, because 2L is the length of the magnet. T1 the oscillation, period of oscillation in the Earth field alone, and T2 in the combined field. So we calculate the value of M by BH. Now the experiment is repeated by changing the distance d. That means the magnet is placed at another distance, d value change. Say initially if it is 12 centimeter, now d is changed to another value, say 14 centimeter. Then T2 value is changed in the combined field. The period of oscillation changed. Then we can calculate again the value of M by BH. So the experiment is repeated 4 or 5 times for different values of d, the distance between the magnet and the center of the SEARLE'S vibration magnetometer, and the mean value of M by BH is determined. Now coming to the tabular column, initially we want to use the box type vibration magnetometer. The box type vibration magnetometer is kept in the Earth's field. We are determining the period of oscillation not once. The period of oscillation is repeatedly determined 3 times, and almost same value we are getting or we will get, and the mean value is determined, that is a time for 10 oscillation. Then that value divided by 10 gives the period t. Then using a vernier we determine the length and breadth of the bar, because for the calculation of the moment of inertia we determine the mass also. Then mass into length square plus breadth square divided by 12 gives the moment of inertia of the magnet. So, the moment of inertia is calculated. Then MBH, that is x, is calculated using the formula 4 pi square I by t square, because we obtain mean t. So, x is calculated. Then using the SEARLE'S vibration magnetometer we want to calculate m by bh. So, initially the SEARLE'S is placed in the Earth's field alone. There also we determine the period 3 times. 3 times the oscillations are noted, time for 10 oscillations are noted. Mean time is calculated for 10 oscillation, that divided by 10 gives the period t, that is t1. Then in order to determine the value of t2, that is in a combined field, a magnet is used and the magnet is placed at distance say 14 centimeter. The magnet is placed in the south of this SEARLE'S vibration magnetometer. We determine the time 2 times, let me determine 2 times. Then the magnet is placed on the northern side with the north pole pointing north. Always the magnet is kept with the north pole pointing north. There also we determine the time 2 times. We obtain almost the same values, we expect that. Then the mean time for 10 oscillation is calculated, then period t2 is calculated. Then using the earlier formula mentioned, we can calculate m by bh. The experiment is repeated for another distance 16, 18, 20 etc. Each time we calculated m by bh. Then the mean value of m by bh is calculated, that is taken as y. Then the moment of the magnet is calculated using the formula root of xy. We already explained, that gives the moment of the magnet, and root of x by y gives the value of bh, the horizontal component of Earth's magnetic field. Now coming to the experimental setup of box type and SEARLE'S vibration magnetometer. Now both these two apparatus are usually placed along the magnetic meridian. So initially we are supposed to draw the magnetic meridian on our table. Now for that we are using a compass needle. When the compass needle is placed on the table, we can see the small magnetic needle at the center of the compass box lies along the north. Now this should be the north and this should be the south, north-south direction. Now with the help of a chalk piece we can mark the north direction, and similarly the south direction and the north direction. Now this is the north direction. Now if we remove the compass box and join these two lines, that should be the magnetic meridian. But since the magnetic needle is very short, our marking may not be exactly correct. So it is better to mark the direction of the aluminum pointer, because the aluminum pointer now is along the east-west direction, because it is pivoted exactly vertical to the magnetic needle, perpendicular to the magnetic needle. So mark the points, the end points of the aluminum pointer first. Mark the end points of the aluminum pointer. Now this is the two markings of the aluminum pointer. Now after removing the compass box, now join that two points. That means the east-west direction that we are getting. Now there should be the west and east direction, west and east direction. Now draw the perpendicular, just check the earlier marking is correct or not. Then we are getting the north-south direction. Now there should be the south direction, and this should be the north direction. Now this is the magnetic meridian. Now this line is the magnetic meridian. Now we can place the SEARLE'S vibration magnetometer and similarly the box type vibration magnetometer along the magnetic meridian. Now we start with the box vibration magnetometer. Now the box vibration magnetometer is kept, its length is parallel to the magnetic meridian. Now it can be rotated, move. Now we want to arrange, there is a line inside the box, and that line is made parallel to the magnetic meridian direction. Now the suspended magnet is performing torsional oscillations. You can see the oscillations. We want to find the time for 10 oscillations. Now when it is coming in one side and going to the other side, coming back, we count it as one oscillation. So we are ready with that. Next time we will start. Now we started, it is going to the other side, coming back one oscillation. Now we want to take time for 10 oscillation. 2, 3, 4 we obtained, 5 oscillation, 6 oscillation, 7 oscillation, 8, 9, 10 oscillation completed. Now you got a time of 47 seconds for 10 oscillations. Now you can continue it for another 10 oscillations. Again find, that is 2. One more you find, that is 3. So 3 times you are finding the time for 10 oscillation. Take the mean. So time for 10 oscillation is 47, 48, etc. Divide by 10, that is 4.7 is the time period of oscillation T, capital T, using the box type vibration magnetometer. Now for using the SEARLE'S vibration magnetometer, we are using the wooden board of the diffraction magnetometer. This wooden board is kept along the north-south direction, along the magnetic meridian, parallel to the magnetic meridian, so that the center of the wooden board is our joint, center of point. It is placed like this. It is placed like this. Now it is parallel to the magnetic meridian and center coinciding with the sun. Now we are keeping the SEARLE'S vibration magnetometer here. SEARLE'S vibration magnetometer. Now we can initially bring it to rest by lowering the brass cylinder and then raising. Now it is performing oscillation. You can see it is performing oscillations. Now when it is performing these oscillations, we can find the time period of oscillations. We can find the time period of oscillations. So we are ready. Now when it is coming in one side, now we are getting the time period of oscillation in the Earth's field alone, that is T1. So we are ready here. Now started, going to the other side, back 1, 2 oscillations, 3 oscillations, 4, 5, 6, 7, 8, 9 and 10. So we obtained 20 seconds. So that is the time period of oscillations for 10 oscillations. We can repeat it one more time, or two or three times we can repeat. We can find the time for 20 oscillation, and from that the time period of oscillation can be determined. Now we want to find the time period of oscillation, that is T2 in the combined field. For that we are bringing a magnet. Now the north pole of the magnet is kept in the north side. Now we want to find the period of oscillation in a combined field. For that we have the magnet whose magnetic moment is to be determined. That magnet is kept in one side, say the northern side, with the north pole pointing north, and now the center of the magnet is at a distance, say 14 centimeter, at a distance 14 centimeter from the center of the SEARLE'S vibration magnetometer. Now the vibration magnetometer is oscillating. We want to find the time period of oscillation. We are ready. Now we will start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are getting a time period of oscillation 10 seconds here. For 10 oscillations the time period is 10 oscillations. Now we can repeat it once again. For the same length we can repeat it once again. So 2 times we are finding. Then this particular magnet is moved to the other side, on the southern side, and kept at the same distance, say 14 centimeter. Now 14 here, the center of the magnet is at 14 centimeter. So D, from the center of the SEARLE'S vibration magnetometer to the center of the magnet is D, that is equal to 14 centimeter. Again north pole is pointing north. The north pole should point towards the north, then only the magnetic fields are combined. Then we are ready. We will start. Started 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here I am getting 9 seconds. Earlier I got 10 seconds. Here I got 9 seconds for a length of for a distance of 14 centimeter. Now we can repeat it once again. So we are having 4 readings, that is T2. Take the mean and find T2, and then you can calculate the value of M by BH, because we know the value of D. D is 14 centimeter. This magnet is having a length of 2L. So, half the length is L. So, we knows the value of L also. So, we can calculate M by BH. Now, we want to repeat the experiment. Now, for that we are changing the distance. Now, the distance D is changed. Now, the magnet is moved to a distance of say 16 centimeter. The center of the magnet is at a distance of 16 centimeter. Then again we can find the time period of oscillation, time for 10 oscillation 2 times, keeping the magnet in the southern side, then place the magnet in the northern side at the same distance 16 centimeter, find the period of oscillation 2 times. Then repeat it for 18 centimeter, 20 centimeter, 22 centimeter. Each time we are determining the value of T2, then knowing the value of T1 we can calculate M by BH. Now, with the help of vernier calipers find the length of the magnet. Now, here the magnet is having a length, we are using the vernier calipers to find the length. Now, the MSR reading is 7.5 MSR reading and VSR reading is 2. Now, repeat it at different positions of the magnet, find the MSR and VSR, then we are getting the length. Similarly, we can find the breadth of the magnet, because we want to calculate the moment of inertia M into L square plus B square by 12. Now, here for breadth MSR reading is 1.5 and the VSR reading is 3. That also you repeat at different points of the magnet, find the MSR and VSR and find the breadth. Now, then the magnet is weighed, this magnet is having a weight of 79 gram or 79 into 10 to the power of minus 3 kilogram. So, using that values we can find the moment of the magnet and similarly the value of BH. Now, let us discuss a sample set of reading we obtain in the vibration magnetometers. Now, first we find the time period T, using the box type vibration magnetometer. Using the box type vibration magnetometer we obtain the T. Now, for that we obtain the oscillations as 49, 51, 50, 3 times we obtained, mean is calculated. So, the time period is 5, time for one oscillation. Then for the given magnet, the length is measured with the help of a vernier caliper, main scale and vernier scale readings are noted, it is repeated 5 times. Then breadth is also noted, we obtain the length as 7.508 centimeter and breadth as 1.508. The magnet is weighed and we obtain the weight as 79 gram or 79 into 10 to the power of minus 3 kilogram. So, the moment of inertia is calculated using the formula M into L square plus B square divided by 12. We obtain moment of inertia as 3.85 into 10 to the power of minus 3. Then the value of MBH now we can determine, because that is denoted as X and MBH is given by the formula 4 pi square I by T square. X, that is MBH, 4 pi square I by T square, substituting the value of T, that is 5, and I that we calculated, we obtain X or MBH as 6.15 into 10 to the power of minus 5. Then for the calculation of Y, that is M by BH, we are using the SEARLE'S. Initially the SEARLE'S is used to find its period in the Earth's field, that is T1. Now, we obtain T1 determined 3 times. Initially we obtain 21, then 20 and 22, mean is calculated, then divided by 10 gives the time for one oscillation, that is period. So, that T1 is 2.1 second. Then in order to find the value in a combined field, we kept a magnet say at a distance 12 centimeter. The magnet is in the south side. Then we obtain the period as 7. When it is repeated again, the time for 10 oscillation is 7. When the magnet is kept in the other side, again it is repeated 2 times, we obtain the time as 7 second itself. The mean time is calculated, then the period is 7 by 10.7. Then we obtain M by BH, is calculated using the formula. Then M by BH is obtained as 6.2 into 10 to the power of 4. Now it is repeated for another distance, say 14, then 16, 18, 20, etc. Each time when the magnet is placed in the southern side, 2 readings are obtained. When the magnet is or 2 readings are taken. When the magnet is placed in the northern side, we are taking 2 more readings. the mean is calculated and period, and m by bh is calculated. Then the mean m by bh, that is actually y, that is equal to 6.227 into 10 to the power of 4 we obtain that much ampere meter square t raised to minus 1. Then we can calculate the value of moment m, that is root of x y, that is obtained via 1.94 we obtained ampere meter square. Then bh is calculated using the formula root of x by y, and we obtain 3.13 into 10 to the power of that is minus 5 Tesla, not 5, that is minus 5 Tesla. So that is value of bh.